is acting on Y?
The weight is acting downwards, 20 newtons.
20 downwards. Then,
The normal reaction upwards, 20 as well.
no, you don't know that yet. Let's call that as N1.
So, but why don't we know that over here?
No. If there you have a single object kept on the ground, then the weight and normal reaction are equal. This is not a single object. You have something on top.
Also, we consider 30 newtons as the
No,
normal
no,
reaction.
no. We'll consider everything later. Just write down the variable N1. That's it. That's the normal reaction. What are the other forces acting on Y?
The frictional force is acting uh, rightwards.
Okay. Let's call that as F1. Any other force?
And the F that they've given, like the force being
Applied force. Okay. Any other force?
not on Y, I don't think so.
So the
See,
friction leftwards, sir, from
so
the box
yes.
X.
Okay, good. So Shaurya, this surface where my cursor is, this is also having friction. So what will be the direction of friction here?
So, not sure.
Okay. For that, focus on X. Tell me the forces acting on X.
Again, like the weight is acting downwards, so 10 newtons.
10 Newton downward and then
Normal reaction, 10 newtons up.
upwards. No. Shaurya, do not equate it for now. Let's write down the variable. I'm writing N2 upwards.
Hmm.
They may be equal, may not be equal, we'll discuss. But we are using the parameter N2. What else?
The tension is there.
Towards the right side. What else?
So the friction is there, but I'm not sure what the direction of that is now.
Okay. So for that, imagine Y is not imagine. Y will go to the left because of this force, right? If Y is going left, which means Y is forcing X to go left side. Yes or no? Sure, yeah. Now for X to be balanced, for to be at rest, what should be the direction of friction?
Same as 10.
Yes, it has to balance the T.
Hmm.
So let me draw. The direction of friction is left, and let's call that as F2. So Shaurya, there are different frictions, F1 on the ground, F2 over here. Shaurya, makes sense?
And F2 is also acting on Y in the opposite direction.
Yes. So F2 acting on Y in the opposite direction. Now, Shaurya, same logic for N2. There has to be a second N2 somewhere
That's on block Y.
in the downward direction. So let me draw this N2 downwards. So Shaurya, this completes the free body diagram. Now for the top
In
blocks,
this
you
question,
can
you don't really need normal and
we don't.
reaction energy, right?
Wait, let me solve this and let's
Yeah.
check later. So Shaurya, for the block X, balance the forces. What will you get? For
Like,
X, if you balance the forces,
T is equal to F2 and
N2 is equal to
10.
perfect. For Y, equate the forces.
F2 plus F1 is equal to applied force.
And
N1 plus N2 is equal to 20.
no. N1 is equal to 20 plus N2.
Downward direction, yeah.
Correct. And N2 is 10, which means N1 will be 30.
Yeah.
Now, what are we supposed to find? We have to find the force F and the tension. So that's it. So now, Shaurya, can you find first F2? What will be the value of F2 using the coefficient of friction? See, F2 will be mu times N2.
So 0.2 times 30.
0.2 times
20, sir, not 30.
N2 is 10.
So then 10, yeah.
Okay.
Shaurya, N2 is 10. So 0.2 into 10. What will be F2 then? 2 newtons.
Yeah.
So if F2 is 2, also find F1. F1 is mu times N1. So 0.2 into
30, so 6.
6. So F1 is 6. That's it. Put the values in this expression.
So 8 then.
8 is the applied force. And what is T? Tension. over
T
here. Look,
equal to F2.
T is equal to F2, so 2.
Mhm.
That is why option A.
So the
And
key was to basically draw like the free body diagrams and equate everything together to find the answer.
yes, exactly. This was indeed a very, very tricky question. So, Parth, you said we don't need friction. How did you solve without finding friction?
Saying we didn't need friction. I'm saying that we didn't need to equate the normal reactions.
Then tell me the approach. How do you do it?
No, sir, it's not like that. I'm just saying that we don't need to necessarily draw the normal reaction diagrams on the thing now because it gets too
If
messy.
you don't draw the normal reaction, how will we find friction? Because
Nee,
friction,
we need normal reaction. I'm saying it's fine if we don't draw the normal reaction on the diagram, right? In the free body diagram
no,
because
no,
it
no,
gets
no,
a
no,
bit
no.
messy.
If you don't draw that, then your equations will go wrong. The mistake which Shaurya did.
Okay.
Diagram is very, very important. That's the step one in solving questions of this chapter.
Okay, sir.
Okay, so Shaurya, check and tell me. In the meantime, let me move to the next. Question number 4.
So for his next question, I had checked. I was going through his questions also. So for this next question, I had an idea. I just wanted to ask. Was this question
One sec,
answered in
one sec.
make sense also?
One sec. For next question, let me put up the question. Hang on. So Shaurya, let me know once you are done.
Yeah, sir. Done.
Shaurya, next time I'd have to create video solutions so that you can revise later and later on as well. Fine, no worries. So option A and B. Hang on, option C and D. Okay, 1 second. Option C and D. Okay, so Ariman, 1 sec. An object falls from rest in vacuum. R is the rate of change of kinetic energy. How does R vary with time? Okay, go ahead, Ariman.
So I first thought it was option B because when constant acceleration, when V kinetic energy V square will be increased, will be exponential increase.
No, but then the problem, I also thought about that firstly.
The answer was
But then
wrong.
the problem is that it's rate of change of kinetic energy.
Yeah,
Na?
so it's
So
about T square. So
it's upon T square. So T square and V square.
Rate of change of kinetic energy means change in kinetic
kinetic energy
energy
upon
yeah,
time. And then so
on
the
time.
slope would be this upon time as well, so it'd be T square. So it's just question wording.
Yeah.
Okay, so then what do we do here?
The slope would have to be this upon T, which should change in kinetic energy upon T square.
Okay, so Ariman, what do I do after this? Rate R is this.
Yes.
After this, what do I do?
So we have our y-axis is this r and our x-axis is t. So the slope would be this upon t. So it would be change in kinetic energy upon t square.
Oh, that way. Okay. So you're using the approach of gradient or the slope. Let me write. So gradient is y-axis upon x-axis. So that will be R upon T, isn't it?
Yes.
So that would mean change in kinetic energy divided by
the t square. Then.
T squared. Fine. Now what do you do?
So since it's falling in a vacuum, the acceleration would be constant. So the velocity change would also be linear. But in kinetic energy, the velocity is velocity square. But also being divided by time square.
Time square. So it should be.
The graph should be linear then.
No, I'm not getting it. So how did you say change in kinetic energy depends on the square of time?
No, so like this change in kinetic energy would depend on like the only thing changing here is velocity because constant acceleration. And so it's 1 upon 2 mv square and the v is increasing linearly. So velocity in kinetic energy would
Time is also increasing linearly. Na? So that's why he's saying it will be balanced out.
That way. Okay. So what is the answer for this?
So option
It should be A.
then.
Okay. It is indeed A. Now, Shaurya, tell me your approach and doubt.
So like okay, I thought that it should be B only, like because in a vacuum, like the velocity is increasing, and then velocity, the square of velocity will also like increase then exponentially. So
Let's see. So
but like
Shaurya,
rate of change.
let's use another approach altogether. Rate is change in kinetic energy upon time. Change is final kinetic energy minus initial divided by time. What is the initial kinetic energy? Shaurya.
of mu
It
square,
is
so
zero.
right?
It is zero. It's
Zero.
falling
Zero.
from rest. Yes, good.
Yeah.
So R will be written as final